This is lecture 38. Okay. And the we had a question that for a n over n output driver, where the cell is shown here, right? And I am using a same control voltage for switching off these. So let me just this thing, this is not a resistor. So when it operates, or okay, let's just okay. Okay, so I'm using a same control voltage for both NMOS for up and down, right? So the question is how can we do it, and I say that this is WN1 by L and WN2 by L. Yeah, you have a ground, so let's say VDDTX is equals to 0.5 volt. In that case, if everything is like having a 50 ohm impedance top and bottom, this is 0.375 and this is 0.125. Now I need to ensure that, okay, for this NMOS up NMOS, let's just call this as M1 and this is M0. For M1, R up is equals to 1 divided by, means I am using a square law model here, by L into V control minus 0.375 volt here minus Vt, right? For M0, which is R down, this is KWN2 by L into same V control 0 minus Vt, right? So you can see that even if I have a different gate overdrive for the two, if you have a different width for both of them, then you can still maintain that R up equals to R down equals to 50 ohm. Yeah. Overdrive for RTN will be same, right? Yeah. So then the thing is, okay, so if you are looking for that particular variation in, so what you do is, let me just tell you. Okay. So in this particular, so this is one of the drawback of this N over N output driver, that unless you use a different control voltage for M1 and M2, okay, you cannot maintain an independent 50 ohm impedance. So what you maintain is this, for a if you are using a same V control, only V control, you are not exercising any control for width right now, same V control for M0 and M1, what you are making sure is that you are having a differential impedance of 100 ohm, not single-ended. I will show you how. So this will imply that you are having a differential output impedance of 100 ohms. What it does is that, so differential output impedance is actually equals, so if I model this particular transistor with the resistance R up and the bottom transistor with R down, okay, and my channel is having an impedance of 2RT, okay. So what we do here is we actually maintain, so this is you can say this is actually VDD and this is ground bottom, right? So what we maintain here is that the looking in impedance here, this Zn should be equals to 100 ohm, which means even in a case when R up is, let's say, 40 ohms, or R up is higher, 60 ohm, and R down is equals to 40 ohm, even then the differential impedance Zn is equals to like R up plus R down. So in this case you maintain a differential output impedance, not a single-ended output impedance. So this is like people use both the cases, where you can have an independent also and you can have the combined also. You get the drawback. If you are not doing it independently, then you will not have you cannot ensure a common mode termination across the different output voltage. Okay. Any other question? Okay. So this high swing voltage mode output driver and low swing voltage mode output driver are clear, right? For you, if I say that you design an output driver with this given swing, you can design it. Do you have any questions on that? Because then we will move into equalization. Okay. So now we move to equalization in voltage mode output driver. So since we have already seen that current mode output driver actually consumes like 4 times the current consumption as what you have in a voltage mode output driver, so it makes sense to do the equalization also in voltage mode output driver. So let's begin with a simple equalization. Let's say H equalizer of N is equals to 0.8. I am just picking up one, that this is the impulse response of the equalizer. So my output of the transmitter is equals to dn convolve with H equalizer of N, which is 0.8 times d of n minus 0.2 times, d of n minus 1, right? So if I want to implement an equalization in voltage mode output driver with one tap, which is shown in equalizer impulse response function, I have to, the output of the transmitter has to be a combination of the current bit and the previous bit, right? Dn and dn minus 1. So what will be the, so let's just write this as y of n. So depending on dn and dn minus 1, your y of n will vary. So let's just pick that dn and dn minus 1 are independently plus minus 1. They are random values. So if I say that this is 1, 1, 1 minus 1, minus 1, minus 1, and minus 1, 1, right? So you have 0.6, in this case 1 here, minus 1, and minus 0.6. So depending on the previous and the current bit, you have to transmit a different voltage, right, in the same output driver. So how can we create a different voltage swing in a voltage mode output driver? We have seen this, right? By using a resistive divider. That is where we started, that if we want to transmit a lower swing, we can use a resistive divider and we can transmit a different swing. We saw that thing independently in a voltage mode output driver, where we say, okay, we want a limited swing, so we fix that limited swing and use the same combination always. The difference here is, depending on the bit stream here, you have to create a resistive divider, or you just transmit without a resistive divider. That's the difference between the equalization in voltage mode output driver and what we have seen before. So let's say we implement this. So consider a case. Let's start building up. When you are having a dnn plus 1 and dnn minus 1, the output swing is maximum, right? So what should be the, I think this will be straightforward. What should be the resistance at top and bottom? So this is 2 times RT. You have R up and R down. This is the case where you will get the maximum output swing, right? What should be R up and R down? RT independently, right? So in this case, you have R up equals to R down is RT. And if you want a minus 1, then you will just have at that time this will be off, and you have R down, sorry, yeah, will it be this way or so? Not this way. This is the opposite case when you are transmitting minus 1, right? Now in place of like positive and negative 1, so let me just write it here, that here V out is equals to plus minus VDD by 2. Now in place of this, I want to transmit a different swing, which is 0.6. This still remains the same. Now I have R up and R down here. So how can I have a different output swing? And we have seen this before, right? Resistive divider. So I have a resistive divider here. Okay, so let me just you call this as, so I will just write it in different manner. I have this R up and R down, just having a different terms. There's a differential negative side, so you have this, right? By using this, you can have a different output swing. Now the only thing is you have to do this depending on the data pattern. So these resistors should be switched depending on the control bits. Okay, so let's see how it is done in a more systematic fashion. So you have okay, so let's say this is R up, this is R down, this is D of n, this one is D of n minus 1 bar, you have D of n bar, D of n minus 1, and this one is, so this is R up, this one is R down, and I have RT. So okay, so I will just use this thing here. This is D of n minus 1, D of n bar, D of n, D of n minus 1 bar. Okay, so in this case, now use take one by one. So in case when you are having a D of n, let me write it here. When D of n and D of n minus 1. So see the case when D of n is 1 and D of n is n minus 1 is minus 1. So I'm using 1 0 and 1 minus 1 like logic and the signal sign. Just one of or the other. So when D of n is 1 and D of n minus 1 is minus 1, or if you want you can say that this is 0 here, right? In that particular case, you see that this switch is off, right? And this switch is also off. Here this one is off and this is also off. So you are having R up and R down in parallel at the top. So the net resistance here is at top is R up in parallel with R down, right? And the bottom also, this is R up in parallel with R down. Okay, and there is no current in the bottom branch, and all the current is flowing through the, this means you can say the current is flowing in this manner. Okay, so you see that you can get a like a positive swing in this manner, right? Now if I have, let's say, look at the case dn is 0 and dn minus 1 is 1, what will happen? It just, the switch size will just flip, and you again have the current, like current in the opposite direction, and the swing is the same. And the impedance, looking in impedance, is also R up parallel R down, that is equals to RT. Okay, now the other case is, let's try copying it this time, hope it works. What is happening? Okay, so let me use the same figure itself. So in case, now I'm just plotting for the case when you are having a, both bits are same. Okay, so this is for the case when dn is equals to 1 and dn minus 1 is 1. So if you look the above figure, only R up is on, switch is on, right? R down is will not be on the top side. R down will be on the bottom side. And similarly you have R down here and R up here. Okay, so the looking in impedance on this side, on the left hand side, is still equals to R up parallel R down, and so is on the right hand side. And because you created a different, you created a resistive divider, you get a different output swing. So this is a very basic implementation of a voltage mode equalization in an, of a equalization in a voltage mode output driver. Now if I say I want to increase the number of taps, what do you think will happen? Let's say I have dn plus 1 also, dn plus 1, dn and dn minus 1. So if I want to, let's extend this design to a more number of taps, what should you do? Another branch resistance, right? That is just like another pair of switches controlled by dn plus 1 on both top and bottom, and depending on which they will control. So the case which we have seen, I think the last time when we worked out, we found so that the current consumption, let's just look at the, this was so you have seen previously that the voltage output swing VOP minus VON is given by 1 by RF minus 1 by R down, right? And similarly we also calculated what will be 1 by R up and what will be 1 by R down. So let's just, this was the, so this is, you see that 1 by R up here is directly proportional to V out, and 1 by R down also, and the current consumption is square proportional to quadratic in relation to V out. Okay, so let's just bring both of these things back, which is here. So if I want to find that what is the total current consumed from the supply when I want to implement the output driver, so this is V out by VDD, and this is, let's say, half. So this is, sorry, This is I total from the supply, and this current is equals to VDD divided by 4RT, and this current was VDD divided by 2RT. This is what we have seen, right? In the previous case, when we fixed our Vout, we were always at the same point, right? When we just wanted a different output swing. But in this case, depending on the data pattern, we will be switching between a maximum and whatever in between the swing is. Okay. So what will happen? So can you comment on what kind of current is drawn from the supply? Is it fixed? Is it varying? It varies, right? And if the current is varying from the supply, what problem can it cause? So think about it. This supply is coming from some regulator or somewhere. And if you are switching the current between two values, it will call like either the regulator has to respond to that switching current, or the large switching currents can also cause more disturbance on the supply and to the other blocks. So the two problems which you see here is this way of implementation. One is that actually you have more current in voltage mode output driver with equalization. So yesterday, after looking at basically high swing and low swing, you said, okay, if I want a low swing, I will always use a N over N. If I want a high swing, I will use a P over N, like a CMOS. Here, no matter which driver you use, if you implement the equalization, your current has to switch the way we are implementing here, right? So, and the other thing, the first thing is the more current, and the other thing is you have a switching current. So these are the two drawbacks of this implementation. Okay. Now so we will go into these drawbacks a little bit later. Now let me ask you, if you are asked to implement this voltage mode output driver with R up and R down, considering that you have to use a different equalization coefficient, because that depends on the channel. You do not know always for sure what should be the coefficient be. What would you do? I mean, how will you design R up and R down? And take a simple case right now, PMOS over NMOS. Okay. You use a lot of segments and you choose between them. So let's just start with that example. So what I do, let's write it as this case is mostly called as uniformly segmented voltage mode output driver. Where you use multiple segments, multiple resistances at both. Right now I'm not showing the switch, so just say you are having total of k segments, and just write it as k times R0 is each value. And similarly you will have at the down k times R0. So this is a single-ended version of the one side of the output driver. Now, depending on process variation, so let me just say, depending on PVT variation, you will choose n segments such that k R0 by n is equals to RT. Okay, and sure you will take into account that even in the worst process variation, my total number of segments are always large enough that I can have the RT as a output impedance. Now these n segments are split into P and Q, where n is equals to P plus Q, such that P goes for main cursor. So are you familiar with the terminology of main cursor, pre and post cursor, right? And let's say here Q goes for post cursor. Okay. So in this particular case, I will choose here. So let's say I choose P and Q. So what is the design schematic? You have all these are controlled by, let's say, Dn, and these are P in number. Then the other one, all these are controlled by D of n minus 1 at the top bar, and they are Q in number, right? Similarly, you will have the downside of this resistance. Okay. So now just consider that your, for example, let's take a number that your n is equals to 16 as per the process variation. Okay. So what kind of resolution can you get on the equalization? Let me rephrase the question, that n is equals to P plus Q. The resolution of equalization will depend on by how much minimum resistance can you change with respect to the total, right? So this is, I can say, the minimum P, or let's say you have minimum value of Q is 1, right? And when Q is 1, P is equals to 15 in this particular case. So the resolution of equalization which you will get is limited to this 1 with respect to 15 or 16, you can call in total. Okay. So if because of process variation, if n changes to, let's say, 14, then what is the minimum Q I can choose is 1 again. In this case, P is equals to 13. Though the resistance values have changed proportionally, now P plus Q is equals to, now 14 is equals to RT cells. Earlier 16 was equals to RT, but it will not maintain the same resolution which you were looking at before. Agree? So in that, if this is the problem, it means whether it's a problem or not, that depends on the design. If this happens to be a problem, then what you do, you always maintain a same ratio of the post cursor to precursor. Means you maintain that resolution. So let's see how you do that. So let's say you are having this so for example, okay, so let me just begin with an example that I am okay. So in this case, I will say, let's say I choose m such cells. Okay. First thing is there are m of these in number, and then multiple such n's I am having. So you can, so the total impedance, if I look, let's say all these are combined in number. So you have, if these are MP, okay, let's say these are Q in number, not Q we have already used. Let's say they are actually K in number. Have you used K? No. Okay. So, and let's say each impedance is equals to R0 something. Okay. So the net impedance of this block is R0 by M, and the total impedance, if I am having Q such cells, then this is R0 by M times K. This should be equal to RT depending on my depending on the process variation. Now, in between this cell itself, like one such cell, all these can be chosen with a mux independently between a dn and dn minus 1. Means there are multiple such mux, you can say, for each cell. Now in this case, so what we do, we choose different number of K cells such that the total impedance is equals to RT. So I am, let's say I am choosing X number of cells which is less than K, such that your R0 by M times X is equals to RT, depending on process variation. Now within each cells, I will choose my equalization depending on the coefficient I want. So that coefficient which I want is like, you can say minimum of post or precursor is 1 out of M. So no matter where the process variation takes it, it will always maintain that particular ratio. So this is one, means here I have shown you a uniformly segmented thing. What is normally done is you make this particular cell as a binary weighted and select between the different between dn and dn minus 1, and then you have these cells copied to select it between depending on the process variation. Are there any questions on this? So this is just to maintain the same ratio of equalization. Okay. And this doesn't basically take you away from the problem of more current or anything, but that problem still exists. So, okay, so let's come back to the problem of more current in a voltage mode output driver while implementing equalization. So we have seen that when you are having a maximum swing, let's just see it simply as a VCM node. Okay, so this is 1 volt, this was RT and this was RT, and the current through this is equals to, okay, let's say this is 0.5. So it's basically 5 milliamperes, right? This was the case. Means this VCM is equals to 0.5 volt. So I is equals to 1 by 200. Yeah. Yeah. So what does LC mean? No, so if I am using a particular cell, so it's like this. Out of the K cells, you choose X cells so that the total impedance is equal to your termination, depending on process variation. Right? That you ensure. Then, out of each cell, whatever ratio of equalization you want to implement, out of M I divide, so M is equals to now main plus post. That always remain the fix. So if I is like this, I can use 1 over 8, 2 over 8 or 3 over 8, whatever I use. But that the whole ratio means I can change always by a delta of 1 over 8. That 1 over 8 is not sacrificed on the cost of the process variation, which you have seen before, that if I use the total number of cells as, where was it? If I use if the total number of cells change because of the process variation, your delta varies, right? Okay, so this is the ideal one where you are transmitting the maximum swing, and when we transmit, let's say half the swing, so still let me just say this is VCM. You have something as R up and R down. What can you comment on the current through this resistor? Let's call it as I signal. What is the I signal? Is it lesser, greater or equal to 2.5 milliamperes? When the output swing is lesser. Huh? Lesser, right? So you are having an I signal which is lesser than 5 milliampere, but the total current which you are taking from the supply is more. That's what we are seeing, right? So can you think of a way to lower the current which is coming from the supply? So here we are basically, what we want to do, if you want to look our goal is lower current from supply and still maintain channel termination. Right? We have to basically satisfy both of these. So you have a fixed supply. You have a question? You have a fixed supply and you want to lower the current under the supply. What's the easiest way to do? Means you have, huh? No, we are not going to current mode right now. Current mode, you see, current mode actually consumes 4 times the current in voltage. Even after the equalization, voltage mode is consuming only 2 times the minimum voltage mode. So we are still not at the place where we are going for the current mode. We want to reduce that only. We do not want to go to 2x or closer to 2x. So you have, see, the supply is fixed in both the cases VDD, right? The current is flowing through the supply is depending on the resistance. Whatever resistance you are seeing. So if I want to reduce the current, the easiest thing is you increase the resistance, right? But the constraining you is channel termination. So let's see, if I ask you, so let's say this is I up and I down. So I can write it that, what is happening? Yeah. So I up is equals to I signal plus I down. That's the KCL, right? Now I want to reduce this and this, but I should have a, first thing is I should have a same signal current because I want a different output swing, right? So let's say, how will I scale I up and how will I scale down I up and I down? Huh? Increase R up. So this basically implies that I go and increase R up and R down. But what I lost? Channel termination. So what can you think that I can still maintain a channel termination now? I want to still maintain a channel termination here. What? Extra, how will you put extra differential termination? So this is the, so if you look at this node particular, let's call this node something as X, then X node you need an extra resistor. for the termination, and we should consume lesser current. We should not consume more current, right? So did you get this logic itself? Like if you want to lower down the current, you have to increase the total resistance seen under the supply. But the constraint is that you still want to maintain the channel termination. Okay. And this is the only node you have. So if you have only one node, you want to change the resistance, it's like you have to put some resistance there only. Okay. So the way it has means it resulted into is that you have R up, R down, and this is RT. You put an extra resistance RSH, and this is VCM. So VCM is, pardon? No, you do not. I will show how you put that up. You do not necessarily put at the receiver. So we'll come to that. So just have a look at this. If I put a resistance here, the looking, see, VCM is a voltage source I am treating it as, so that's incrementally grounded. So if I want to look Z in, let me just carve out these, and I want to look Z in here. My Z in is equals to R up parallel R down parallel RSH. It's called as RSH, short form of R shunt. That's the terminology used. So now you get an extra resistance to have the freedom to change the termination, and you hope that by using this kind of resistance you can get a lower current or something. No, so RSH is in parallel to, yeah. So I think you look at the implementation, not just like how it is terminated. I think then it will become clear. Yeah, that's I will make it clear. So that's the confusing part here. So let's say right now I am only using a MOS to tell that this is a resistance and a switch both. We have this thing, right? So now does it become clear? So the RSH resistance is still coming on the transmitter side. The 2RT termination is on the receiver side. So we just remove the channel to have a more simplified picture. So if I look, the input impedance looking in, Zn, right? That will be equals to 2 RSH in parallel with, what will be this in parallel with? 2 RL parallel R down. Is 2 RL parallel R down? Okay. Right? Yeah. Yeah, that RSH will consume current. The whole thing is whether the total current is going to be more or less. The thought is that you reduce the total current by increasing the impedance, okay, and then you have the channel term, and then whatever the current is getting is split into RSH and RT, the total current is still lesser. And our goal is also to have the current which is actually constant. Right now we are looking for the aim that we have a current which is lesser and also current which is constant, because if you do not have a constant current, that will be causing a more supply current supply ripples, right? So if I want to do, like, since I have more freedom now with RSH, so let's see what are my goals. I want channel termination which implies that 1 by R up plus 1 by R down and 1 by RSH should be equal to RT. Okay. The other thing which I want, that my current consumption should be independent of the output swing, because I do not want any supply ripple. So that is D of I supply by D V out should be equals to 0. And V out, you know, what V out do we want to transmit? That depends on equalization. So the other thing that should come first, that V out dependent on equalization. So actually we have, yeah, V out independent. I do not think you can have it as independent of R. It's difficult. So it's like this. You want a different V out. So we were doing this thing. When we want a different V out, we were having R up and R down, completely dependent on that, right? And if you say that V out is getting independent of RSH, then we are more or less leading to the first place itself. What here the aim is that I out should be independent of the V out, that the current remains fixed, and current remains lower also. Whether it's a lower or not, that you can always, actually this particular equation, right, I up and this particular equation, if you find that I should be able to scale my I up down and even then maintain a signal current, you can find that exist values I up and I down for which you can do that. That's a very simple equation which you can get it. So you can use like same, let's say you are having a 1 volt swing. When you reduce the 1 volt swing to 0.5 volt swing, 0.5 volt supply, your I signal will become half. So when I signal becomes half, at that time you find that whether I up can be scaled or not. So we have these three guidelines to design the output driver. So let's go in one by one. And it's already 50 or something, right? Okay, so you will start on these three equations and see how you can design the voltage mode output driver with the fixed current. Okay.